Hi, welcome to the ninth session of group theory. We are going to continue subgroups. So this is going to be subgroups 2, something like section and subsection. Okay, so we are going to look at few more examples and lot of things which are usually not done in courses, but I'm sure by the end you will appreciate and you will begin to enjoy a great deal. Why such things were never taught. Okay, and yeah, it's a happy Diwali. Actually, Diwali was yesterday. We released a subgroups yesterday, and today we are going to continue with group theory too. But as you know, for business people, this is account opening day, right? Well, I am also in business, namely the best wealth you can ever create, education. So I am in the field of education. That's my business. Of course, this may not give materialistic money, but it brings a lot of wealth, the goodwill from you guys. Okay, let's continue. Okay, so let us first. I hope just make sure I started the thing. Okay, good. So let us first start with the some of the standard example one always says, so subgroups examples. Continue. Okay, the standard example one always has is the following. Look at all additive groups Z. This is a subgroup of Q, all additive groups now. That is groups under addition, right? This is a subgroup or this is a subgroup C, right? That is the, you want to be precise, you should put like this. This is a standard example because take any two rational numbers, add. First notice that 0 belong to each of the thing. Okay, the additive identity. Then whenever you have an x in x and y in z, x plus y is in z, right? And similarly minus x is in z. So if I take two rational numbers, see what you have to do, I have to show z is a subgroup of q, right? That means take two any element x and y in z, then I have to say x plus y is actually an integer. It may be, it is not a some kind of a fraction. Okay, it is a regular integer. And similarly, if I take two rational numbers, their addition is again a rational number, and additive inverse of any rational number is again a rational number. And similarly, R set of real numbers, how do you consider? You remember, you consider C as collection of x plus iy, where x and y are in R, right? Therefore, I think of x as x plus I times 0. Therefore, R is first is a subset of C first. And second, take any two real numbers, then it is a x plus y. Another one is y plus I 0. And what is the, how does the complex addition go? Complex addition goes add the real part, that is x plus y, and then add the imaginary part, that is 0 plus 0. That is x plus y plus I times 0. Therefore, this is again in R. You understand? So we are identifying R with complex numbers as a subset under the addition. Whenever x is a real number, I identify as x plus I 0. Is that clear to you? That is the only subtle point you have to learn. Okay? Right. And if you want the same way, I can also say subtle point. If you give 2, I want to consider as a rational number. So you either I can consider as 2 pi 1 or something. Because if you want to write q as a rational number, the standard definition will be set of all p by q. Okay, p and q are integers and q not equal to 0. Right, I have to write like this. So in that case, I am still identifying z as a subset of q, whereas whenever in integer n is given, I write it as n by 1. Therefore, it's an element of q. Is that clear? Pause, review, proceed. Okay, right. The next important thing is slightly abstract example. I am sure all of you have learned linear algebra, right? And also, therefore, V is a vector space. Let us say over R, it has two operations, not necessarily not two operations. There are two things: V cross V to V, and dot product, which is R cross V to V. Now, this is a scalar multiplication, not dot product. Scalar multiplication. Dot operation is what I wanted to say. This is the vector addition, right? So under vector addition, V with this is an abelian group. The usual axioms under addition about addition or vector addition, okay, prove that it is an abelian group. Okay, please review this. Okay, right. Now suppose W is a vector subspace. See, remember V is a vector space. You have the notion of vector subspace. When do I say W is a vector space? Whenever x, y is in W, x plus y is in W. And then for every real number alpha in R, alpha times x is also in W. Right? So this condition proves, and remember when alpha is minus 1, you already know minus 1 times x is the additive inverse. This is the additive inverse. Okay, we need this condition. Are you following? Therefore, if W is a vector subspace, then W is a subgroup of V under addition. Do you understand this? The only subtlety is, okay, the vector subspace definition involves two conditions. First condition is whenever x and y are in W, x plus y is in W. Okay, that shows W is closed under addition. Then I have to show whenever x is there, its additive inverse minus 6 is there. How am I going to prove that? That is where you use the second condition. Okay, if alpha is a real number, alpha times x is in W. In particular, when I take alpha equal to minus 1 times x equal to the additive inverse of x. Okay, those who have not learned linear algebra vector space thoroughly, this is the important thing. Okay, minus 1 times x is a vector. This vector is nothing other than, call this vector y. This is the unique vector such that x plus y is 0. This y is what we denote by additive inverse. Okay, so make sure you understand these things. These are the things which people don't explain thoroughly. Okay, spend some time, learn it. Okay, right. Now I want to go to the very important thing. Okay, okay. Right. I hope you enjoyed my vector subspace example. Yeah, good. Okay. Also, usually people will accept, okay, R is a subgroup of C, Z is a subgroup of Q, etc. We try to explain what it is. Whereas by definition, Q is a subset of R. There is no problem. The only thing is you distinguish elements of real numbers. One is rational and one is irrational. Whatever is not rational, Q is a subset of R. If X belongs to Q, it's called rational. If it's not in Q, it's called irrational. That's the only way we define, right? Okay. Don't get confused. Just think about, okay? These are the subtle things one has to think, learn to understand, appreciate, okay? And you will see that you are much more matured mathematically this way. Good. The next example is a very important thing. I found many students don't know this. See, there are very few groups for which we know all the subgroups. You understand this? That's something very interesting. Okay. One group for which we know all the subgroups is this additive group of integers. Okay. Right. The second group is cyclic groups. What we are not yet defined, we will do it later. But these are the two groups we know all the subgroups. Very rarely we know all the subgroups. It's a very complicated object. Okay. Collection. So let us do that. So the next example is what are all the subgroups? That is, I want to list all subgroups of Z under addition. Yeah. Notice that for any natural non-negative integer n in Z plus, we define nz, which is Hn. What is this? This is multiples of m, where m is over Z. For example, n is 2, it is all even integers. When n is 0, then it is only singleton 0. Which 0 is singleton 0. Right? When n equal to 10, these are all multiples of 10. Right? If you want 10n, 10m, where m is in z. Is that clear? What we want to show, these are all the subgroups. Claim if H is a subgroup of Z, then there is a unique n in Z plus so that H is Hn. That is, if H is a subgroup of Z, then there is a unique non-negative integer n so that all elements of H are multiples of n. Okay, understand the statement? To prove is easy. Let us say suppose I have 4. Okay, now what is H4? H4 consists of 0, 4, 8 and here minus 4, minus 8, etc. Right? Suppose I have an H, I want to say it's H4. Okay, how will I identify this 4? You understand the question? I want to say H is, there is a unique integer, that integer is 4 and H equal to H4. However, where will I find it? We work backwards. Suppose it's actually H equal to H4, how will I locate H4 here? How will I locate 4 here? Look at all non-negative elements here, positive elements here, okay, and look for the minimum. Okay, are you following me? That's what you are interested. Okay, so prove if H equal to singleton 0, then H is H0. Okay, therefore assume H is not equal to 0. That means what? There is an A in H so that A is not 0. Where is A? A is an integer. Now A is non-zero, therefore either A or minus A is a natural number. You understand this? Yeah. Therefore, if I look at H plus equal to set of all x in H so that x is positive, then the H plus is non-empty. Do you understand this? If H is not 0, then there is a non-zero element. Therefore, A or minus A has to be a positive integer. Right? Therefore, the set of positive integers H plus is a non-empty set. This is all I am saying. Is that clear to you? Now I can use well ordering principle. Okay. What does it say? If S is a non-empty subset of natural numbers, then there exists a least element in N. Of course, it's unique. What does it mean? It says there exists an M in S so that for all N in S, M is less than or equal to N. And this M is unique because if there is an M dash, then M must be less than or equal to M dash because M is the least element. M dash also less than or equal to M, therefore equality holds. Uniqueness is easy. Do you understand the statement? Okay, if you have gone through my elementary number theory, this is the first starting point of natural numbers. Okay, right, now let's go to H plus. So H plus is a subset of natural numbers. It's non-empty because either A or minus A belongs to A. Let's say A is positive, then A belongs to this. Sorry, A belongs to H plus. Right? Therefore, it's non-empty. Right? Therefore, by well ordering principle, okay, there exists an N in H plus so that here N is the least element. H plus. Yeah? You agreed? So this is what I said here, right? How will I locate 4? Look for all positive elements here Look for the least element. Then what do I want to say? Every element here in H is a multiple of 4. Right? Now what do you want to show? We claim that my H is nothing other than Hn. Right? Notice that since n belong to H plus, which is contained in H, all multiples of n belong to H. Because n plus n belong to this, minus n belong to H, and so on. Therefore, all, do you remember where we looked at exponents? Okay, for the indices law, right? There, if A belong to H, A power n belong to H, because H is a subgroup. Okay, in case you don't have no idea, let me just take a digression. Suppose H is a subgroup of G and A belong to H, then A power n belong to H for every integer n. Why? Because when n equal to 0, then it's clear. A power 0 by definition is identity and H is a subgroup, therefore A power 0 belong to this. Right? The next, since A belong to H, A squared belong to H. That is A squared is A times A. Whenever A and B belong to H, A times B must be in H, therefore A squared is in H. Therefore by induction, so I assume n is a natural number, I have proved A to the power n belong to H. Then I want to prove A to the power n plus 1 belong to H. How do I do that? A to the power n plus 1 again by our law of exponents, okay, law of indices, we know it is A power n Ta. Now this is an element of H, this is an element of H, this is an element of H given by hypothesis. A power n belong to H, this is by induction, and there are two elements of H, their product must be in H. So we proved for all natural numbers it belongs to this. Okay. The same way when n is negative. Look at B equal to A to the power minus 1, that belongs to H. And what is B power n? We remember this is A to the power minus n, which is same as A to the power minus n. We had already proved law of indices. Okay. Yeah. There we proved it. Therefore, by the same thing, B power n belong to H for all n natural number. That is A to the power minus n belong to H for all n. Therefore, I have proved A to the power n belong to H for all n in Z. Okay. Please pause, review, proceed for the digression. So what we proved, so let us make it as an important observation. If H is a subgroup of G and if A belong to H, then A power n belong to H. This is true for all n in Z. This is the observation. Yeah, you see that? When you do, then only we remember we have not done something, okay? But you have to be alert, you have to keep your eyes open and brain should be working, so you should spot the issues. Is that clear to you? That's a very important thing. Repeatedly we are going to use it throughout any algebra course. Okay, it's good that I remembered, I did it. Okay, now let's go back to the earlier result. So what did I want? H is a non-zero group, subgroup of the additive group of integers. Then I found out there is a least positive integer n in H. Then I want to show H is H of n. That means every element of H is a multiple of n. What is obvious? Since n belong to H, all all its powers. In this case is addition, right? In this case, A to the power n is nothing other than n times A. Sorry. n to the power m is m times n. Do you understand? M plus n plus n plus n m times, or minus n plus minus n plus minus n m times. Okay, these are the analog of A to the power n. Okay, they all have to be there. Are you following? Okay. So let's go back. Therefore, since n is in H, Hn must be a subgroup of is contained in H, because any element here is m times n. Okay. Okay, this is the additive notation. In multiplicative notation, n to the power m, that is n times n, okay, or minus n times minus n. But all those things in the addition, we had already seen that, right? In whenever addition, a to the power n stands as na. Okay, this is clear. Now, therefore, what is that I have to prove? Now, if you give me an element a in H, I want to know whether a is in Hn. Right? That is whether a is a multiple of, that is a multiple, a is a group element, multiple of n. To answer this, what do you think I have to use? Yeah, remember I told you divisional algorithm is the most important thing. That is why I suggested, advised that all of you should go through the lectures on ENT, elementary number theory. Okay, so what we want to do is give me any a in H, I have to say it's a multiple of n. Remember, n is a positive integer, right? Therefore, I can write by division algorithm. I can use division algorithm to divide a by n. That's what we are going to do. So we use division algorithm to answer this. So by division algorithm, a is going to be some q times n plus r, where r is 0 less than or equal to r less than n. Yeah, right? Now notice that n belongs to H. Therefore, q times n, which is a multiple, this is intuitively n to the power q. Okay, right? That also belongs to H. Now a belongs to H, qn belongs to H. Therefore, what is the additive inverse? Q1 inverse. This is additive inverse minus qn, right? That also belongs to H. Therefore, a belongs to H, minus qn belongs to H. Therefore, a minus qn belongs to H, right? But what is a minus qn? A minus qn is r. Therefore, this implies r belongs to H, right? Now, notice that r is non-negative, right? Suppose r is not equal to 0, then r is positive. But and r is positive, therefore r belongs to H, and r is strictly less than n and is also positive, right? That contradicts n is the least positive element in H, right? This contradicts which n is the least positive element. Therefore, we conclude r has to be 0. That is, my a is q times n, and therefore a belongs to Hn, right? Therefore, what have we shown? We have proved H is Hn, because H is contained in Hn and Hn is contained in H, therefore H equal to Hn. Yeah, so this is, as I said, the first and the simplest and perhaps one of the very few cases where we know all the subgroups. Okay, right. So what have you found? In the additive group of integers, any subgroup is multiple of a single non-negative integer. Finished. Is that clear? Please enjoy this. In fact, if I remember right, I created a single video just for this subgroups of Z plus. Okay, it may be there in the YouTube. That was done about 2-3 years ago. I don't remember. But anyway, go through it. Is that clear? Very good. Right? Now we are going to do, after this very concrete example, we are going to do a little bit of abstract example, and we are going to get some very beautiful applications of that example. Okay. Maths is interesting if you are willing to think. Okay. So now I want to do intersection of two subgroups. Suppose H1 or H and K are subgroups of G. Some group now. Okay. I want to know what happens to H intersection K. I want, okay, H intersection K. I want to claim this is also a subgroup of G. Right? Do you understand this, what it means? Okay. Right. This means first it's non-empty because since H and K are subgroups, E belong to H and also it belong to K, therefore E belong to H intersection K. Therefore this is non-empty. Next, suppose A belong to H intersection K, A, B belong to H intersection K, then A, B belong to H. Therefore, the product AB group product belong to H. Similarly, AB belong to K. Therefore, the group product belong to A, K. This implies AB belong to H intersection K. And suppose A belong to H intersection K, then A inverse A belong to H, therefore A inverse belong to H. A belong to K, therefore A inverse belong to K. Therefore A inverse belong to K intersection H. H intersection K. Right? Therefore H intersection K is a subgroup of G, P, R, P. Okay? In something similar you might have already seen when you learn linear algebra. If V is a vector space and W1 W2 are vector subspaces, W1 intersection W2 is again a vector subspace. Yeah? Do you remember that? It's exactly similar. But we can actually do more than this. But then it requires a little bit of set theory. Again, my pet theme. Okay, you should always watch the 4 foundation videos, okay, in the website. Please learn that, because basic set theory functions, just because you learn in high school, it's never taught precisely. When you want to use it, people are at a loss. Okay, please go through it. Many times I have spoken about it. Okay, let us do that. I will quickly review. I will do that here. Now let us, okay, digression, set theoretic digression. Digression, double S. Okay, suppose X is a set, non-empty set, assume, of course. Okay, and A, okay, A is a collection of subsets of X. You understand this notation? That is, if you say A belong to this, what does it A? This A is a subset of X. It's a collection of subset, not all subsets, perhaps a collection. You understand? Then I want to know what is meant by this. This is a notation. Intersection of all elements in A. Right? Are you following? If I suppose this my script A consists of only finitely many elements A1, A2, An, where each A is a subset of X, you know what is intersection A1, A2, intersection An. Right? The same way I want to do. So this is a subset of X. So when does an element X belong to this subset? This intersection, if and only if for all A in A, script A, X belong to A. That is, look at this. If my script A is A1 to An, what does it say? Script A in A, this is set of all X in capital X, so that for all A in A, that is for all A in what? A1 to An, X belong to A. That means X belong to A for all I. Do you understand? Okay, please pause, review, proceed. So, for precision, I will assume this is a non-empty collection. Therefore, what we want to do is if H, okay, if script H is a collection of subgroups, a family or collection of subgroups, then this H naught by definition is intersection H in script H is a subgroup. Okay, right. In the set theory digression, suppose I is a non-empty set, call it index set. Something. It has nothing to do with X or Px. Maybe some, right? Now, for each I in I, suppose I am given A, which is a subset of X, which is an element of Px. Then I can define intersection A, I in I of this. This is again the same thing, X in capital X, so that for all I, X belong to A. Okay. So the family in this case was not an index family. This is a family of subsets. Here the family is indexed family of subsets. Now do you realize such things? Yeah. Those of you who feel little bewildered, okay. My request, advice to you is go to the foundation course where I talk about this kind of stuff. Okay. A family of subsets, index family of subsets, their union, their intersection, etc. Right? Please learn that. When you want to do mathematics at BSc, MSc level, especially algebra, analysis, etc., you have to learn them. Unfortunately, these things are never taught. Okay. Of course, many of our MTTS teachers across the country, they do teach, others don't. Okay. Right. Let's go back. Now, let us look at I have H, a family of subgroups of a group G, then H naught is a subset, sorry, ordinary H in script H. This is a subgroup of G. The proof is exactly is same. Suppose A and B belong to H naught, that means A and B belong to H for every subgroup H in this family H, right? Therefore, A, B belong to H. For which H? For every H in script H. Therefore, A, B belong to H for every H in script H. Okay, that means that is the definition of it belong to the intersection. That means H naught. Do you follow that? Okay, rewind if necessary. I will put a PRP, rewind and hear my voice and again stop it, pause it, review it before you go further. The same proof works now. If A belongs to H naught, let us look at A inverse. Okay. Now, say that means A belongs to H for every H in script H. Since A is a subgroup, that means A inverse belongs to H for every H in script H. But this is the definition of A inverse belong to the intersection of H in script H. But that is H naught. Therefore, H naught is a subgroup of G. Okay, if you please go through, if you find it a little difficult, okay, just to assume this, go ahead. I'm going to give you a very concrete application of this, right? Okay, let us see that. How much time I have? About 35 minutes. Okay, I have to another 25 minutes. Okay, let's go back. So, yes, sorry, there was a slight disturbance. We shall continue. So we will give an application of these two things. Okay. First application. Okay. Recall for each, let G be a group, A is an element. Recall we define what is meant by centralizer of A in G. Centralizer of A in G. This is set of G in G such that GA equal to AG. That is, we collect all elements that commute with G. We have seen that CGA is a subgroup of G. Okay, we had already seen it. Now, let me look at this. See, therefore, I have index family C, G, A. Okay, as A varies over G. You notice that? Like, this is my, if you want to call it H, A equal to CGA, centralizer of A in G. Therefore, HA is a collection of subgroups indexed by elements in G. Yeah. Now, let H equal to intersection of HA or H0 as we called it, A in G. This is a subgroup. We already know that, right? Now, what is this? What is this subgroup? Yeah, is the question clear? Let's look at. Suppose G belongs to H naught. What does that mean? This is the intersection of CGA. A varies over G. This belongs to this. That means if only G belongs to CG of A for every A in G. Right? This means G commutes with A for every A in G. What does that mean? This means G lies in the center. Center of G. Remember, center of G is the subgroup G in G, so that for all A in G, GA equal to AG. That is, all elements, this commutes with each and every element. If G belongs to this, that means G commutes with each and every element A in G. Right? Therefore, we have found that the intersection of CGA as A varies over G is the center of G. Okay, P or P. Right? Isn't it very interesting? See, it's not only theory, we are also giving immediately applications. Okay, so that you understand the theory better, and also some of the concepts like intersection, etc., indexed family of subsets, what is the intersection, all these things you learn thoroughly. This is the advantage. Okay, if you simply learn a subject for exam point of view, grades point of view, you will not enjoy, you will not learn, you cannot retain. Okay, good. Now I want to give another application. This again, this is an abstract application is what we gave just now. What is that? It is intersection of centralizers of A as A varies for all of G is nothing other than the center of the group. What is the next application? That's something very interesting. Yeah, this is again usually not done. Okay, that some of the very interesting things, because people want to finish the syllabus theory, big theory, they just ignore a lot of very nice examples. Okay, this is one such. Let's look at it. Now a second application. So let me time to change my thing, right? What is the second application? Now we have seen in Z under, okay, all the subgroups are Hn, where Hn is, yeah, n times Z, where n is in Z plus. Okay, any subgroup is of this form, right? Now I can ask a question. Suppose I have HA, suppose A, B are in Z plus, assume they are positive actually. A, B, or N. Okay, that will be more interesting. Now this is the subgroup, right? Therefore, it's a subgroup HC, right? It's a subgroup. This is a subgroup of Z plus, right? You understand this? Intersection of two subgroups is a subgroup. Therefore, this is a subgroup. But I know every subgroup is of form Hn. Therefore, there is a C, unique C, so that HA intersection HB must be HC. You understand this? What is this C? Can we identify this C? Is the question clear? Now do you accept it's a very concrete application? Right? Any subgroup is of the form multiples of A. Another subgroup is of the form multiples of B, where A and B are natural numbers. Now HA intersection HB is again a subgroup. Therefore, it should be multiples of some C. What is that C? Yeah, think about. I'm sure all of you will get. Okay, I will explain the first line. You should be able to guess the answer. Now, suppose some integer n belong to HA intersection HB. What does that mean? N belong to HA and n belong to HB. But when n belongs to HA, that means what? N is a multiple of A. Okay? And n is also multiple of B. Right? You understand? Right? Now suppose HA, I'm working backwards. Assume HA, I know this must be some HC. That means C belong to HC. That means C belong to HA. Therefore, C must be a multiple of A as well as B. That is, A is a common multiple. Come on, now you should be able to guess. What should be C? I'm sure all of you know the answer, right? At least, okay, your gut feeling should give an answer. What is that? It is the least multiple. C must be the least multiple of A and B. Now we want to prove that. Yeah, and we will get something much more interesting. Yeah, we had already seen that. Do you remember? If you have gone through my LCM, okay, and GCD LCM, you would have known that. Okay, let us quickly see that. Therefore, because C must be because C is the LCM of A and B. Okay. Now, CV belong to HC. HC is HA intersection HB. Therefore, C is a common multiple. Right? Now, HA intersection HB is HC. That is no doubt, right? But how did I find the C? C is the least positive element. Least positive element of HC. You follow that? Please understand. Don't give up. Yeah. HA intersection HB is a subgroup. This is a subgroup of Z. Therefore, it must be of the form HC. Is that clear? Right. Now C belongs to HC. Therefore, C belongs to HA, HB. That means C is a multiple of A and multiple of B. Therefore, it's a common multiple of A and B. Right. Now, how did you find the C? This C is nothing other than least positive element. Now, start with any X or call it K in HC. Since HC is equal to HA intersection HB, okay, K is also common multiple. Right? K belongs to HC, but HC is HA intersection HB. Therefore, K is a multiple of A, K is a multiple of B. Therefore, K is a common multiple of A. Therefore, HC, okay, is contain in common multiples out of A and B, right? And C is the least element here, is the least positive element, right? And what is LCM? LCM is among the common multiples of A and B, the least is the least common multiple. Therefore, C is nothing other than LCM of A and B. Pause, review and proceed. Yeah, did you appreciate that? Okay, we use the way how we find C in HC. That C is the least positive integer. Now every element of C is a multiple of common multiple of A and B. Therefore, C also belong to that, and C is the least positive element. Therefore, C must be the LCM of A and B. Beautiful, right? Right? See, just check whether these things are proved in any book. This is very interesting. Very good. Now, let us go ahead. Okay. Now, we want to, maybe I should again. Yeah. Now, I want to give yet another beautiful application, okay, of the result intersection of any family of subgroups is a subgroup, right? That's what we did, right? If script H is a family of subgroups, intersection of H as H varies over script H is a subgroup. We saw that, right? We already gave one application, right? The center is intersection of centralizer subgroups. The second application we gave is HA intersection HB in Z plus is HC, where C is the LCM. Now third, again an abstract application. What is the application? Now suppose G is a group, right? Now I can ask you a question. Suppose you give me an element A in G, okay? Whether there exists a subgroup H such that A belong to H. Is the question clear? That is obvious because G itself is a subgroup. Take K equal to G, then A belong to H, right? Is that clear? Right. So what have we shown? Suppose script H is H, where two conditions: H must be a subgroup of G and A must be an element of H, right? This family of subgroups is not empty because G itself belong to this. Is that clear? Yeah. Now let H naught be the intersection of H as H varies over script H. So try to understand, just don't play with only symbols. Therefore, what is H naught? H naught is the intersection of all subgroups H so that A is an element of H. Is that clear? Yeah? Just don't look at only the symbol. Try to understand. H naught is intersection of all subgroup H such that A is an element of H. Right? Okay. Is that clear? Therefore, I know H naught is a subgroup. This we already know. Right? And I claim H naught is the smallest subgroup. That contains A. That is, if K, what does it mean? If K is any subgroup of G such that A belong to K, then H naught is contained in K. That is, you understand? When I say it's the smallest subgroup that contains A, that means among all subgroups that contain A, K naught is the smallest. What? That means if K is any subgroup which contains A, then K, H naught is subset of K. That is very clear because if K has this property, then K has to be in script H. You understand? Therefore, if you give me any element G in H naught, that G belong to H for every H in script H. In particular, G belong to K, because K is one of them. That means every G in H naught is an element of K, right? P or P. Make sure if you are a beginning BSc student and if your foundations are not very thorough, these are the things which will be slightly challenging for you. Okay, review this, and believe me, it will pay a lot of dividend if you watch my foundation videos. Okay, it's some kind of advertisement, right? No problem. I'm not charging any money. Okay, right, go back. Is that clear? Okay. So what we have proved? So what have we proved? What is proved is something very interesting. Given any A in group G, there exists the smallest subgroup H so that contains A. So how do I get this H? That is, or if you want to call it H naught, that contains H. How do I find H naught? That is, H naught is nothing other than intersection of all H, where H is a subgroup of G and A belong to H. Okay, this is the collection. This is the family we denoted by script H. Right. The next question I want to ask. So we proved the existence. It's not A, it's actually the smallest subgroup. H0 containing A. Right? Is there a concrete description? Is the question clear? Yeah? So we shall get a concrete description. Okay, it will be very different from some of you might already learn group theory. Okay, you will see how we arrive at something which you already know. Okay, by asking questions. Okay, it's not somebody we give this and say something happens. This is what usually maths is taught like a religion. You accept it, then it will work. Right, let's go. Okay, so we know, let H naught be the smallest subgroup containing A. My handwriting, all of you know, it's very bad. I don't want to write much. I'm reluctant. My handwriting can be better, but anyway, right? Now let us try to understand. I know A belongs to H naught, right? If A belongs to H naught, we already saw H naught is subgroup. That means A power n belongs to H naught for every n integer, right? We had already seen this. Right? Therefore, let us look at, okay, K, which is A power n, n varies over Z then. So this K is contained in H naught. Is it clear? Now let us look at, take any two elements in K, they are of the form from A to the power n into A to the power m. Right? A to the power n, A to the power m. What is their product? A power n. This is by law of indices A power m plus n. But m and n are integers, therefore m plus n integer, therefore it's again in K. Do you understand this? This is law of indices, right? Next, if A power n belong to K, I want, what is A power n inverse? That we had already seen again by law of indices, is A to the power minus n. Since n is an integer, minus n is also an integer, therefore it's again in K. Yeah, again law of indices. So what do you conclude? K is a subgroup. K is a subgroup of G. But does A belong to K? Yes, A belong to K, right? Because n equal to 1, right? A belong to K. Therefore, K is a subgroup that contains A. But what do I know? K is already contained in H naught, but H naught is the smallest subgroup that contain A. Therefore, H naught should be contained in K, right? K is a subgroup of A. And what is meant by smallest subgroup? It is if K is any subgroup which contains, if K is any subgroup that contains A, then H naught should be contained in K. Therefore, H naught is contained in K, but K is already contained in H naught. Therefore, K equal to H naught, right? Therefore, we found out the smallest subgroup that contains A as a concrete description. It is all powers of A. Okay, this is what in textbook they call it. Hey, what happened to that? Where did I write? Yeah, here it is. Yeah, so this is what usually one calls is cyclic subgroup generated by A in G. So in classical thing, the authors and teachers and textbook, they will define this and show that this is a subgroup, then call it cyclic subgroup. Yeah, but you realize how you arrived at it? Isn't it interesting? You found something very interesting. What did you find? It's not only cyclic subgroup, it's the smallest subgroup which contains A. Right? Very good. Now, there is one more question I can ask. Suppose G is already finite group. A is an element of G. Then, if I look at H naught, which is A to the power n, where n varies for all integers, this is a subset of G. Therefore, this must be finite. Right? Even though it looks A power n as n varies over Z, Z is infinite. Okay? There are not infinite number of elements. Right? So, do you think we should understand it better? We will do it in the next session. Okay? Take care. Stay safe. We will meet again.